In this session, we will talk about decision trees. The talk is divided into the following essential learning outcomes. You should be able to outline the fundamental principles of decision trees to represent medical problems. You should be able to explain and discuss the characteristics of tree splitting, stopping criterion, and pruning. And you should be able to describe what overfitting means in this context. There are numerous examples of decision trees in healthcare. For example, to predict the probability of mortality of gastric cancer patients, predicting cesarean delivery with a decision tree model, diagnosis of myocardial infarction, identification of signals of possible adverse drug reactions, and using modifiable risk factors to predict major depressive disorders at a 4-year follow-up. If you look into PubMed, you will also find plenty of other decision tree models applied in healthcare medicine. Why are there so many decision tree models in healthcare? The reason is it's relatively fast compared to other classification models once it is trained and useful for prediction. It's simple and easy to understand both for clinicians and for patients. And for that reason, decision tree models, despite a lower performance score, for example, that can be achieved in comparison to support vector machines or artificial neural networks, it is widely used. It can be converted into classification rules. Training data could possibly contain errors or missing data, but decision trees are robust against that and can deal with errors or missing data. A learned function can be represented by a decision tree. It's successfully applicable to different medical cases and, for example, for diagnosis, for therapy, for prevention, and for rehab. The generic problem setting is the same as for any other classifier. We have a set of possible instances, X. We have an unknown target function, F, which transfers our instances or our feature vectors into class labels Y. And we have a set of different functions which could possibly satisfy this condition. Our input are training samples where we already know the output generated by the target function. Our output is a hypothesis H that best approximates the target function F. How would you construct a decision tree? First of all, you have to know there are 3 types of nodes. You have a root node that has no incoming edges and 0 or more outgoing edges. At your root node, all your data sets will be provided to the decision tree at the first start for training. You have then internal nodes, each of which has exactly 1 incoming edge and 2 or more outgoing edges, depending on the individual configuration of your decision tree. You will have a leaf or terminal node, each of which has exactly 1 incoming edge and no outgoing edges. How is the classification performed? An instance is classified by starting at the root node of the tree, testing the attribute, moving down the tree branch to assign classification with a leaf node. In this particular slide, you can see a decision tree illustrated using a space view. On the left-hand side, you can see a first test. For example, consider you have 2 features, x1 and x2, and you have 2 class labels, 0 and 1. If you were to test your first feature, x1, with the first condition, if x1 smaller 0.5, if that is true, you go into the left part of your decision tree, and then you further test, for example, x2 smaller 0.3. If that is also true, you end up in the terminal node R1. Likewise, you would do it for the other areas, R1, R2, R3, 4, and 5. If you were to visualize this in a plot, consider you have on the right-hand side a 2-dimensional feature space, and in that plot, all the different decisions can be characterized by individual areas. And that is quite simple for a two-dimensional plot and for two-dimensional features. In a three-dimensional feature space, you can also see that as individual objects, which are further described by the conditions set out by your decision tree. How would this possibly look like for a real example in medicine? Consider you want to find out if a patient has a prolapse or a no prolapse, and if the patient has intersystolic noise and myocardial infarction and heart malformations, then he or she has a prolapse. That's your first rule. Secondly, if the patient has intersystolic noise and myocardial infarction and no heart malformations, then he or she will not have a prolapse. Looking at the individual decision tree, you can see that you have an attribute test at each internal node. And this is used to further break down your feature space into an individual sub-feature space to derive a class label. And your class label here is a binary class label, binary classification, prolapse or no prolapse. Another example in ophthalmology. Consider you want to see whether a patient needs contact lenses or not. If you look at the individual lookup table here, you can see 24 different instances, 24 different cases, and you have a four-dimensional feature space, taking into account the age of the patient, her spectacle prescription, whether she is astigmatic, or her tear production rate. For the first feature, we have three different categories, 3. For the next one, we have 2. For C, we have 2, and then we have another 2. If we want to look at the overall number of rules, we calculate this by 3 times 2 times 2 times 2, and that makes 24. And that's why we have a fully completed rule-based lookup table with 24 instances. If you were to expose this to a decision tree algorithm, it can also generate automatically, based on this lookup table or training set, a fully complete decision tree. As previously mentioned, you can also convert a decision tree into rules, and you can see this with individual Boolean operators on the right-hand side, that the decision tree was spelled out and explicitly written down individual rules. By the way, we have here 3 class labels. We have fit hard lenses, we have fit soft contact lenses, or do not fit any contact lenses. So that are 3 different class labels that we have to decide for. Another example would be to predict cesarean delivery with a decision tree model. Consider we have a huge training set of patients who previously had a C-section or no C-section based on individual clinicians' decisions. If we expose an individual decision tree algorithm to this training set, it would, for example, construct different splits, and based on these splits, you have a decision tree. The only difference here in that individual visualization is that this is not visualized in the classical decision tree, but by individual rows. But in fact, this is just a different way to express a decision tree. You can also redraw this into a classical decision tree. Creating a decision tree is quite complicated. One of the reasons is that there is an exponentially number of decision trees that is possible to be created from a given set of attributes. In computer science, we say that is an NP-complete problem, a non-polynomial problem. So only a heuristic will help us to create a suboptimal decision tree in polynomial time. And for that reason, there are a number of different algorithms. This is the pseudo-algorithm to create a decision tree. Let's call the method partition. The input is data S. If all points in S are of the same class, then your algorithm can stop and you can return. In any other case, for each attribute A of your training set, do a split based on the attribute A. You need to do a best split to partition S into a subset S1 and S2. What is a best split? A best split could possibly be defined by the purity measurement, entropy, or Gini index. Once you have done these splits, you recursively call the function again. Partition on subset S1, partition on subset S2, and so on. First of all, let's look at the purity measurement. So entropy is one possible measurement to measure the purity of an individual split, Gini index, or the classification error. Normally, within Orange, for example, you will see that the entropy or Gini index is a valid hyperparameter for your decision tree. Both serve the same purpose. For example, the entropy for where if you have a data set where you have a 50-50 split for a binary classification problem, your entropy would be maximized with the value 1. Your Gini index would have a maximum of 0.5 if you had a similar split of 50-50. Looking at this individual example, and this will take you a lot of time to find this, if you use the previous equations, and if you look at this individual count of this binary classification problem, you will end up with a different Gini index or entropy. Let's focus on Gini index and entropy for now. That individual split is a very clean split. So, for example, we have all 6 class labels are of class 1. So Gini index is 0 and entropy is 0 because that is a very pure data set. Consider we have 1 instance of class label 0 and 5 instances of class label 1. We have a slightly increased Gini index and a slightly increased entropy of 0.65. And if we were to have a 50-50 split, 3 instances of class 0 and 1, our Gini index is maximized with 0.5 and our entropy is maximized with 1. Please recalculate this by using the equation for Gini index and entropy to come up with the same numbers. What is the stopping condition to terminate the tree growing process? One possible strategy is to continue to expand until all records belong to the same class or all records have identical attribute values. What you could do then, you can do pruning. Why is that important? You want to avoid overfitting of the tree and to improve your classification performance on unseen data sets, your test data set. There's no point to create a decision tree which perfectly predicts all instances of your training set because it has to perform quite well on unknown feature vectors, on unknown feature sets. So one technique is to grow a large tree and prune back it to optimal size by removing nodes. In that particular illustration, you can see how overfitting would possibly affect your decision tree learning. Consider you have on the x-axis size of tree or the number of nodes. The more nodes you develop, the better your training set will be predicted for the decision tree. So, for example, the accuracy goes up and up and it will at one point become 1 because your decision tree perfectly predicts the data of your training set. But at the same time, if you were to expose your decision tree to a test data set, your accuracy drops because your decision tree was overfitted on your training set and is not able to predict instances on unseen data. So what have we learned in this session? We talked about the fundamental principles of decision tree representation for medical problems. We explained and discussed the characteristics of tree splitting. We talked about the different types of tree splittings based on purity measurements such as Gini index and entropy or misclassification error. We talked about the stopping criterion and pruning. And we talked quickly about what overfitting means in this individual context.